great pleasure to welcome Peter Dueben here to give a talk in our AARMS Scientific Machine Learning. Just a few words. He finished his PhD at the Max Planck Institute of Meteorology in Hamburg in 2012, then became a postdoc at Oxford University before joining the ECMWF, working in various positions at the ECMWF, and is now the head for a coordinator of machine learning and AI at the ECMWF, the European Center for Medium Range Weather Forecast. So really excited to having him here and tell us about the activities that they are doing regarding machine learning for weather prediction. And I do hope you can share your screen, Peter.
I can try.
Let me make you the presenter. Oh no, it's all good.
Yeah, I can see. Sure. Yeah, I hope you see my slides now.
So, yeah, I can see your slide. It's all good. So yeah, we are just eager to hear you talk about this. Thank you.
Yeah, thank you for inviting me. Is it correct to assume that that not everyone here is from weather and climate, right? You're basically spread over different disciplines, right? So
yes, that's quite fair to assume.
Yes, perfect. And we are a fairly small round of people here. So if you have any questions, please interrupt as we go ahead. I have a lot of slides. And if we don't get to the end of the slides, that's no problem at all, but only as long as you have asked questions in between. So I would, yeah, please go ahead and ask questions. It would also help me to adjust a bit the pace of the talk. So I'm talking about machine learning for weather and climate predictions, and I'm working at the, as Alex mentioned, at the European Center for Medium Range Weather Forecasts. And this is just one slide of introduction, what we are and what we do. So we are also known by this kind of a bit strange acronym ECMWF. And we basically a research institute, but we also are operational weather prediction center. So we perform twice a day weather predictions that are going into what we call the medium range. So a couple of days into the future, but also monthly and seasonal predictions. And we're focusing on global predictions. So we have the entire Earth, basically. We are independent intergovernmental organization, and we have a lot of member states supporting us that you can see on the right. And we're now based in Reading they're the headquarters, but we also open like 2 new facilities, one in Bologna and one in Bonn. We have something like 350 members of staff. And as we do operational predictions, we also have 2 supercomputers that we're looking after because you need the compute power. And finally, we also have what we call the integrated forecast system, which is one of the leading global weather prediction systems of the world. So it's a global weather model in principle. So why would machine learning help to perform weather and climate predictions in principle? So the first question to ask is obviously, why is it actually difficult to make weather and climate predictions? And I like to show the figure on the right here, because it already tells you a lot of the problems that we have as part of the story. So one problem that we have if we want to predict the global weather is that the Earth that we need to basically model is extremely large. So basically, even if you run the fastest supercomputers in the world, we can only run a grid scale of something like a kilometer or more, which means that a lot of the small scale processes, like for example, clouds, are not going to be resolved within the simulations. And that's a problem because, as you know, clouds are quite important for local weather. So basically, this means we have a numerical model and we need to represent subgrid scale features, for example, as parameterization schemes. And we need to somehow add them to the simulations, even though they cannot be properly resolved. Then you also know about the butterfly effect, probably, that basically we have a chaotic system here. Errors are growing exponentially, which doesn't make it easier to make predictions. And also the model is, the Earth system is actually complex in the sense that a lot of different components are involved. So in the figure here, you will see basically the land surface. You need a land surface model. You see the ocean. You need an ocean model. You need the atmosphere model. You need cloud physics and chemistry representation. And you need topography representation, and all of those different features need to interact with each other. And they do this on 2 different time scales. And also, due to the complexity, we basically end up with a model that has more than 1 million lines of code. So it's quite a beast, quite a difficult setup in principle. And this basically results in the fact that we are quite good in forecasting a couple of days into the future. But as you probably all know, a 10-day weather forecast is difficult because the quality is at one point reducing, obviously. So it's just a very complex nonlinear system. And it's often difficult to simulate something like this with conventional models. But on the other hand, we have a huge amount of data available. So we are collecting something like several hundred of millions of observations into ECMWF every day for the globe. And we basically have also a huge amount of model data available that we could in principle use to learn something about the systems. And we're talking really about hundreds of petabytes of data that are lying in our data archive. And if you now put those 2 points together, so you have a very complex nonlinear system, and on the other hand, you have a lot of data, then it is kind of obvious that if you had a tool that could learn from data how a nonlinear system would behave, would be very useful. And machine learning can actually provide this tool. Machine learning can be used to learn information from a large amount of data that can be very complex. And naturally, there are kind of a lot of application areas for machine learning across the workflow of our numerical weather prediction system. Why should we look into machine learning right now, and why haven't we looked at it, let's say 30 years ago? The plot on the right is showing you the time evolution over the last couple of decades on the x-axis, and the y-axis is basically the sustained performance that we had at our supercomputers, and the boxes in the plots are the different supercomputers that we were using on site at ECMWF throughout the years. And you will see that in this plot there's basically a linear growth of the compute capacity, and it's a logarithmic plot. So this is an exponential law, and this is nothing else than Moore's law and the exponential increase of compute power. But at the same time, we also have the blue line in this plot. And the blue line is now showing you the size of the data archive that we had at ECMWF. And you will see that, again, it's a linear function. So it's an exponential growth. And this basically means like we had an exponential growth of data capacity over the last couple of decades. And this is continuing. And basically, this means there is a lot of information that we can gain from looking into, and machine learning can really help here. Then there has been an enormous amount of progress regarding compute hardware for machine learning. So this is a slide that I've stolen from Thorsten Höfler, where he tried to kind of collect all the different companies that are involved in machine learning, like building dedicated hardware for machine learning. And you will see that the slide is very busy, and the slide is getting busier every day. So there's more and more hardware for machine learning. And it's even the other way around, that if you have basically a multi-billion-dollar industry behind machine learning, then this means that machine learning is really dwarfing all the high-performance computing applications right now. So if there's new hardware coming out, it's almost certainly going to be customized towards machine learning, which means that even if you have no interest in machine learning whatsoever, if you want to work with high-performance computing, you would need to think about machine learning one way or the other. Then also, there has been an enormous amount of progress regarding the software. So there are really nice tools available right now that allow someone who has never worked with machine learning before to write a very complex neural network structure, for example, within a couple of hundred lines of Python code. So it's very easy to actually get started with machine learning nowadays due to this increase in software availability. And then finally, the increase in knowledge. So there are something like 100 new papers coming out of machine learning and artificial intelligence every day. So basically nowadays we are much more able to build very customized solutions for specific problems. And this also helps you to really build the right machine learning tools for your application. I guess you will know most of this already because you're also working in machine learning. But anyway, I think it's good to set the scene for a seminar talk like this. Why now also specifically for weather and climate? We're currently at in the process of building what we call digital twins of the Earth. So the European Union is going to fund the so-called Destiny project, and Destiny is going to really build very high-resolution models and very high-resolution data assimilation, with the aim to actually build like a digital representation of the Earth, which is almost indistinguishable from the real world. And I've shown you this figure here before, but what I haven't told you is that there's actually two halves of this figure, and one half is basically giving you information from observations from satellites, and the other half is giving you information from a very high resolution model simulation that we performed on the Summit supercomputer. And what you should hopefully see is that there's almost no difference between the two. So it's very difficult actually to distinguish which one is which. And you can give it a shot if you want and tell me which one is a model and which one is observation, but you don't need to if you don't want to. And at the same time, it's also interesting times because our models, as I said before, are very bulky and large and mostly written in Fortran code and kind of not really very easy to write model. It is Nope, right is the observation. And the bulky, they're very bulky and large, and this basically means that it's very hard to port those models, for example, to GPUs and other accelerators. And this is very important nowadays with the heterogeneous hardware coming up. And therefore, we need to rethink about ways how we kind of build our models anyway at the moment. We need to reshape those models to be more portable to different hardware structures and so on and so forth. And therefore, we call this that we basically need to have a digital revolution of Earth system sciences to some extent. And machine learning fits perfectly in here because machine learning will help you to port models to GPUs. It will help you to be very efficient on supercomputers and so on and so forth. And I will talk a little bit more on this later on.
Sorry, maybe a quick question.
Of course.
So you're just talking about like having models in Fortran code, but on the other hand, developing like these machine learning things in like PyTorch or basically in Python. Is there a problem, or it doesn't matter?
Yeah, perfect question. It is a problem in the sense that it's a hassle and it's effort. So it is kind of a bit difficult. It's more difficult than people may think to actually take a model like IFS and then in Fortran and then basically couple in Python and machine learning tools that use, for example, TensorFlow and other libraries. So it is a problem in a sense that it's annoying, but it's not a fundamental problem. I mean, we're basically searching for like generic solutions to make this coupling possible. And once it's possible, it should be implementable easily for different applications across the workflow. So it's not no fundamental problem, but it's an annoying thing to kind of to think about and work on. Does it make sense?
Yeah, thanks.
Okay. So the big question is that I'm asked quite a lot, and I keep this slide now for almost 2 years, so the situation hasn't really changed too significantly in the last 2 years. The big question is really, what will machine learning in 10 years look like for weather and climate modeling? So I brought you this slide that is showing you a grayscale, and on the left side of the scale, you basically have the notion that machine learning will have no long-term effect whatsoever. It's basically just a wave coming through, and in 10 years we're going to talk about quantum computing, but not anymore about deep learning because it's just hasn't worked out well. And on the right side of the scale, it's basically telling you that machine learning will replace almost everything, and we were not going to do anything else in machine learning in 10 years from now. And it's a grayscale because there are a lot of applications where it's kind of more likely that machine learning will basically make a big difference, and there are other applications where it's kind of unlikely that machine learning will really kind of replace everything. But if you talk to different senior scientists in our domain, some of them will tell you that we are on the left side of this figure, and some of you will tell you that we are on the right side of the figure. So it's not really certain right now where we're going to end up with, and that's kind of the message that I want to get across. That basically the uncertainty range for this question is still ongoing, and we still don't know exactly how we're going to work with machine learning in 10 years from now. But let's just assume for now that we're going to be on the right side here. How would the world with just machine learning and nothing else look like for weather and climate modeling? So we basically made a test where we tried to basically replace the conventional weather forecast model by deep learning and do nothing else in deep learning. And this is not a bad idea in principle because, as I told you before, we have this enormous amount of data available that we can train from. So how far do we get? We made a simple test configuration, and we retrieved historical data for basically weather situations of the past over the last couple of decades for a field called geopotential height at 500 hectopascal. And it's kind of quite a standard field for meteorology, and it's global and it's two-dimensional. And we now coarse grain the field to a coarser grid, and then we basically try to predict the update of the field from 1 hour to the next using deep learning. So you literally have a stencil of the that you walk through the grids, and then you basically update the field given a deep learning tool where you learn the update from the field from 1 hour to the next. It's fairly simple to realize, and it's basically a pure data science problem. So no physical understanding is required. But once you've done this, you can actually make a prediction. So you can literally look into the future using your deep learning tool. And this is what we came up with. So here you see the global maps. And one side is showing you the ERA 5, like the truth that we're using. And the other side is showing you our deep learning model. And even the domain scientist couldn't tell you which one is which. So in principle, the deep learning tool is actually doing surprisingly well, in particular because this is my first application for deep learning ever. So even someone who has never worked on machine learning before could actually do something useful. So the neural network is picking up the dynamics nicely, and also the forecast error is looking quite good. So on the right side here, you have the L1 forecast error plotted against time for a 5-day prediction. And the black line here is the neural network forecast. And the blue line is the forecast of a very, very, very coarse resolution dynamical model, something like a model that we would have worked with like 30 years ago. But the two models are actually not too different in terms of the complexity. So if you compare like with like in terms of complexity, actually the neural network is doing quite well. Surprisingly well, actually. It's still far away from our operational predictions that we have nowadays, the magenta line, but this line down here has 1 billion degrees of freedoms, and these lines here have a couple of thousand degrees of freedom. So it's an unfair comparison. And also there's a lot of progress going on. So a lot of groups have built much smarter machine learning solutions than we had that we used. I think Alex also has done some work, for example, on physics-informed networks and stuff. So, I mean, there are a lot of people working on basically bringing down this line closer to the operational forecast. And the question is like, how far do we actually get? So will this be the future for medium-range weather predictions? And it's quite unlikely that this is going to happen. First of all, the simulations are still changing. So I don't think any group has actually managed to kind of find a dynamical model from neural networks that is actually consistent in terms of that the atmosphere would always look the same at the beginning of the forecast and at the end. And that's very important because you want to represent all the features realistically within the model. But also there's not enough data available. So you only have something like 40 years of training data, which means that it's just not enough to actually train a model that has 1 billion degrees of freedoms down here. So it's even though there's a lot of volume available, there's not enough independent weather situations if you want to train something like this. But still, there are petabytes of data, so I may be wrong. Maybe if you listen to the same talk in 10 years from now, we're going to do only machine learning. Who knows? And it's actually quite true that this is already kind of machine learning is already replacing some of the models. And in particular for what we call nowcasting. So in nowcasting, you basically want to predict precipitation events, for example, 1 or 2 hours into the future. And if you do this, you can learn straight from observations. And you can basically be much faster as well than conventional tools, because here it's really, really important that the model is basically producing results in an instant, because you only have 1 hour to communicate the results to the general audience. And there's, for example, the MapNet model by Google, where they show that for nowcasting application, actually, the machine learning model on the right is performing much better in comparison to the ground truth than the NOAA forecast, which is kind of the state of the art over the US. So for nowcasting, machine learning is already replacing models to some extent. And also, if you think about like very long lead times, like, for example, a couple of months into the future or even multi-year predictions into the future, then everything turns into a statistical problem. You don't want to represent the entire atmosphere anymore. And then also machine learning is going to be better. So there's a paper by Hamed Al, for example, where they show that machine learning can really be very interesting at these timescales as well. And climate is a big question. There are good reasons why machine learning should be good for climate, because it's also a statistical problem. But on the other hand, there are also good reasons why machine learning is not going to be good for climate. For example, if you train your machine learning tool on nowadays climate and then climate is changing, you may get a problem, because often the machine learning tools can't extrapolate into unseen future. So if suddenly in Newfoundland, basically the weather is going to change significantly because the Arctic is warming up, then this may not be represented by the machine learning tools that you've based on today's climate. So this could be a huge problem. So having talked about all this, the all-in approach, let's just kind of talk quickly about the challenges that we have at the moment when we talk about machine learning for weather and climate predictions. The first challenge that we have is that there's often a different philosophy between domain scientists and machine learning scientists. So domain scientists like to think about physics and physical equations and these things, and machine learning scientists like to think about supervised learning with input, output, and loss function. And it's often difficult to kind of build trust between the two communities and to kind of foster communication. Then there's also often a set of different tools that is used, for example, Fortran and CPUs in the domain, and Python and GPUs for machine learning scientists. And again, we need to learn how to bridge basically the two communities and how to merge the tools. Then often off-the-shelf machine learning tools are not really sufficient for weather and climate applications. I will come to this point later. We still also need to learn how to really scale up our applications in terms of the compute power. I mean, we can't nowadays already build billion degrees of freedoms machine learning models from petabytes of data, but we would want to. If we would want to learn really how to make use of the big data we have available. Then it's often questionable how to integrate machine learning tools into the conventional numerical weather prediction workflow. So this concerns Rüdiger's question as well. It's sometimes more difficult than you may think to combine the two worlds, but it's work in progress. And then finally, also, the machine learning tools need to be reliable in terms of we need to make sure that they don't need to extrapolate, for example, into totally unseen weather predictions, because then they are likely not to work well if you, for example, use deep learning. So a couple of challenges. And the next couple of slides are actually about the question like how can we address those challenges, and how can we start from this slide where you basically have the impact of machine learning gauged between the two extremes. And the question is like, how can we make sure that we actually can make the best use of machine learning in the next 10 years? And that's kind of part of my job description as well as a machine learning coordinator. I need to kind of really think about what we need in terms of machine learning and how we get it. So where is machine learning used at ECMWF at the moment if we are not convinced that it's going to replace everything for medium range weather predictions? This plot here is showing you the workflow that we have at ECMWF. So we basically get observations in, then we perform a process called data assimilation, where you bring the observations and the model trajectory together. And you do this to generate new initial conditions that you can then use for your numerical weather forecast. So you run the model into the future, and then you get output data and you do post-processing and dissemination of the results. And underlying is this big high-performance computing and big data processing infrastructure that is required for each of those individual tasks. And I've asked around at ECMWF who is working on what kind of application regarding machine learning. And this is what I basically came up with in terms of the responses. So this is a very busy slide, and I'm not going to go into any details, but what you should see is basically that we have on the order of 30 applications throughout the workflow where we are exploring machine learning right now. And the message I want to get across on the slide is basically it's not going to be the one killer application for machine learning. It's more like going to be a lot of different applications across the workflow that we are interested in. And those applications are also in different phases. So some of them haven't even started yet. So there's also the blue boxes here. Some of them are ongoing, the green boxes, and some of them already have published papers, so they're kind of well advanced. But there's still one box missing, and Alex asked me about this before. We don't have many applications yet in operations. So that's kind of the fourth box that should kind of appear there within the next 1 or 2 years, where we are using those tools operationally. Okay, how do we get there? How can we actually make the best possible use of machine learning in our institutions? And first of all, we need to get organized. So if you have all those application areas, you want to also make sure that you kind of organize the work well between the different groups and teams. And therefore, we have written what we call the machine learning roadmap. It's kind of an outline for how we want to work with machine learning in the next 10 years at ECMWF. And if you're interested, it's available online. It's something like an 11-page document. So if you're interested, have a look and let me know what you think about it. Then we're also partnering up with a couple of institutions, like, for example, Atos and NVIDIA, so they know how to use machine learning and they can help. And we have what we call the Center of Excellence, where we basically team up with them and have a couple of projects together. So the idea is also here to work on the objectives that I have on the slides, and you will basically see that those objectives fit well to the challenges as well that I have described earlier. Then it's also about learning how to really make use of machine learning in the best possible way. So the Earth system is basically multi-scale. So what this means is visualized in the figure on the left. Here you have on the y-axis, you have, I think, 11 orders of magnitudes in time, where there are important features going on in the atmosphere. And on the x-axis, you have, 9 orders of magnitudes in space that are important for the atmosphere. And in the center of the figure, you have the different phenomena that are actually working on those scales. So for example, ENSO is working globally on multi-year scale, and there you have planetary waves that are on the order of months that are also globally. Then you go down in terms of the scale in time and space, and you reach at one point the micro scale that is even also important for weather and climate modeling. And what this means is that if you want to actually look into the future with a weather forecast model, you need to represent some of those scales explicitly, but some of those scales also implicitly in terms of parameterization schemes. And you need to allow for scale interactions. How would this look like for a machine learning tool? in a machine learning tool, there are actually ways how you could do this. So think, for example, of an encoding decoding network where you have inputs at a higher resolution, and then you basically encode things. You reduce the number of degrees of freedoms. You go to something like a very small number of degrees of freedoms in the code, and then you increase fidelity again toward the high resolution output. And by doing this, you kind of can already entangle like a scale interaction into it. You can think about it as like high fine resolution input, coarse resolution code, and very fine resolution output again. And so there are ways of how to basically encode scale interactions into neural networks as well. And we have recently done a study where we looked into downscaling. So what we basically did was we took weather forecast simulation at 50 kilometer resolution, and we downscaled it and tried to perform mapping from the 50 kilometers to a 10 kilometer precipitation field that is coming from observations. So we tried to basically post-process our model fields. And we did this by using an encoder-decoder network, a so-called conf-GRU network. And it's actually, this is illustrated here. So you have time on the x-axis, and you start from 6 hourly fields of the model, and then you go to daily precipitation fields, and then you actually encode further into weekly, and then you kind of decode again into daily, and then you have the output on the daily scale. And you have cross interactions here to basically not use the high frequency information. But it also turns out that conf-GRU is fine, but you can also add on top of this self-attention mechanisms. So basically using a tool that comes from language processing to further basically represent these time interactions and just learn how the different points in time interact with each other by using a language processing tool. And then again, we basically learned how to improve our predictions. So it's really about, we need to learn how to use those tools that are kind of well known in the machine learning world, but we also need to learn how to use those tools in a physical context. Next one, how can we combine our models actually with machine learning? So I told you before that we perform data simulation. So we have observations coming in, and we have a model trajectory, and then we try to combine the information from the two to generate initial conditions that we can then use for predictions. And the important step is here that within data simulation, the model trajectories of very short-term predictions and the observations are representing exactly the same weather phenomena. And they are so close to each other that you can actually use data simulation to learn the model error. So you can run the model for 12 hours into the future, and you can diagnose the difference between the model and the observation. And if you're good enough, you can actually learn the model error within this 12-hour window. And that's great, because if you have learned the model error in principle, you can also correct for the model error within simulation. So you can be bold enough and basically say, like, okay, if I can give a machine learning tool a physical situation of the atmosphere, and I know the error, what it looks like, I can learn the mapping between the physical situation and the error, and I can use this to predict the bias, the model error, and then I can put this error back into the model simulation and basically correct for the error as the model is progressing. We did this together with NVIDIA. So we basically looked into temperature fields in the stratosphere, so very high up in the atmosphere. And we basically performed data simulation, and then we diagnosed the model error. And then we used the machine learning tool to learn the model error given a specific state of the atmosphere. So on the left side here, you see a time evolution of the model error. That is basically the target that is coming out of data simulation. And on the right side, you see what the neural network is predicting. And this is now a three-dimensional prediction of the atmospheric error, which is kind of quite something new. And you see the pattern is reasonably close. It's actually closer than we expected it to be. So we are very happy with those simulations in principle. But now the question is, if you now perform an update of your model, what happens then? Because if you update your model that you use for operational predictions, your error pattern is going to change. And we update our model twice a year. So the results that we had so far are great, but they are obtained by using training data of 12 years for a specific tool. And that's a lot of data, and we can't generate so much training data for a normal conventional model upgrade. So there we only would have something like half a year of data. So the question is, can we actually update our machine learning tool as we kind of change our model cycle and as we change this error pattern? And the results are on the bottom here. So we have the the new machine learning target for the same time period. So it's a new error pattern that's coming because you have a change, performed a change in the model. And on the right side, we use transfer learning to actually try to learn how the new error is kind of relating, or to try to learn the new error given a very small amount of data that we had available. And what you see is the differences are now bigger between the left and the right side. And also there's still very much similarities between the top and the bottom, which means that basically we need to learn how to do better here. So it's one thing to kind of learn really very interesting machine learning tools, but it's another thing also to kind of make them useful within the normal cycle upgrades of the model. And it's something, it's work in progress, I would say. So something that we need to learn and you need to kind of look into a little bit more. Then also we need to build tools that make it easier for the domain scientists. So if a normal standard domain scientist would start to work with machine learning applications, they would typically spend something like 80% of their time on data processing, and that's a lot. So basically, you would need to try to kind of collect the data, and then you would need to learn how to read them into Python, how to optimize the memory and cache efficiency, and so on and so forth. And then you would do some work with machine learning code, and then you would also spend a lot of time on post-processing and plots and stuff like this. And the idea of this tool Climate Lab is actually to make this easier. So to really reduce the boilerplate code that is required on the scientist side. So the introduction of the data should be much more simple, and then basically the machine learning scientists can focus on the machine learning code, and also post-process should be supported. So it's basically a way of trying to improve the data efficiency and the data loading in a way that the domain scientists don't need to care too much about writing boilerplate code. Another thing that is important for the domain is also to think about so-called benchmark datasets. So what is a benchmark dataset? A benchmark dataset is basically a statement of a specific application within weather and climate that is using machine learning. Then the ability to make the data available online, to also provide Python code and Jupyter notebooks that can basically load in the data and use the data. Also the diagnostics that are required to really make quantitative evaluations of metrics of tools that are developed for this problem. Also reference machine learning solutions should be given, and then also help with visualization, diagnostics, and robustness tests should also be provided. And then finally, if you're really keen, you can also add some information about computational benchmarks. And if you put all this together, you have what we call a benchmark problem. And that's useful because it basically means that you have isolated your machine learning problem from the domain scientists. And now every machine learner can just kind of look into the benchmark data set and should be able to reproduce what you've done so far, and basically to make magic in the machine learning side of things. So the usefulness comes basically because there's a quantitative evaluation of machine learning approaches that basically makes it possible to compare results between different groups and different approaches. But also it reduces the data access and the for the domain scientists, all the hassle with the data again. And finally, no, not finally, but also there's a separation of concerns. So machine learning scientists can really look into domain science problems without being specialists. And then also it basically helps to understand how to kind of use machine learning tools at scale, because you can also compare different results in terms of high performance computing. And finally, also by generating data sets, benchmark data sets, you also reduce the pressure on data handling systems. For example, at ECMWF, we provide access to petabytes of data, and this is a huge effort. And machine learning scientists are very greedy, so they want to have a lot of data and download a lot of data. And if they basically, everyone would build up their own data sets, they would touch a lot of tapes in the archive, and this would generate a lot of pressure on our data system. On the other hand, if you have a data set that a lot of people using at the same time, you can actually provide it on very fast access routes like disks, and where people can get it very easily, but also they're not going to then touch the same tapes ever again. So that's also useful. So we have a special issue on the on benchmark data sets. So if you have any ideas about benchmark data sets in weather and climate, let me know. And also we basically came up with a list of different application areas where we think that machine learning tools, machine and benchmark data sets should be developed within our domain. So there's a lot of work to be done in principle. We need to learn how to use machine learning at scale. So there are projects, for example, like the Milestone project, where we basically try to develop machine learning tools, but then also software solutions to make them really trainable on petaflops. and then also identify what hardware is kind of best to work with it for those specific machine learning applications in our domain. Okay, it's kind of now like a bit of a break point. So what's going to come next is that I'm going to talk you through specific application areas that we're looking into ECMWF. So I've basically now have another, I don't know, 10 slides or something like this on specific applications that I could guide you through. Or you can ask questions now, and we can talk about the first part of the talk if you want a little bit more, but that's up to you. Are there any questions?
Yeah, I would have another question.
Yeah, sure.
Earlier, you presented this, so you trained basically a machine learning model on previous climate or weather data, and then compared it to a simulation. And we saw basically that they were quite similar, but how similar were, for example, the conserved quantities or like the conservation laws?
Good question. I would say not too similar. So I don't think we have. I don't think many people have actually thought about putting specific constraints on, for example, energy conservation or momentum conservation or something like this into the mix. And naturally, if you just learn something and apply it, you will get issues with conservation laws in principle. But on the other hand, I have to say that that's probably not the zeros order problem that you will hit. I think the bigger, I mean, if you're talking about, for example, a 5-day weather forecast, if you really manage to kind of get rid of a significant amount of energy that you will see the difference, then you're in trouble anyway, right? So at this stage, I think conservation is probably not the biggest problem. And but it would be interesting to kind of consider more how you can actually put constraints in to make sure that energy is conserved, because the closer you are to reality, with those constraints, the more likely it's also going to be that you get good predictions, I guess.
Okay, yeah. I mean, I guess you already answered the other question related to that, because I was always wondering, like, how important is in the end, like, conserving these properties? Or, I mean, I guess there's some sort of like balance. Of course, if it's like completely off, then nothing makes sense.
Yeah, I mean, there are different conservation properties in the Earth system, and the thing that you need to get right is that the error in the conservation that you're doing needs to be smaller in comparison to the time scale the conservation is acting on. What I mean by this is basically, if you think about mass conservation, the time scale where the conservation is acting on is basically infinite. So you really want to get mass conservation right. You don't want to lose mass of the ocean or the atmosphere in a 10-year simulation. So that's very important, but it could be fairly simple to actually enforce this by, for example, by just checking every once in a while how much mass you have lost and then reinstating it. For energy, it's different. For example, energy is acting on a time scale of something like 20 days. So the atmosphere is heated up and losing heat into space, and there's a time scale of something like 20 days of a repetition period, basically. And this means that if you are losing a significant amount of energy in 20 days, that's bad. But if you your energy conservation is reasonable for 20 days, it's not so bad, because the atmosphere is not a closed system anyway. And it's worth noting also that I don't know a single weather and climate model that is actually conserving energy, for example. I think all of them are actually not conserving it in principle. So it's not that we need fundamentally to conserve energy. It's just that we need to make sure that our loss or gain in energy is actually kind of small in comparison to the forcing period. This makes sense.
Okay, yeah. Thank you.
Any other questions? Nope. Then I'll just continue until you stop me and talking about specific application areas for machine learning. One of them is that we want to speed up our simulations, and we basically do this by running our model forward and then storing input and output pairs of specific model components, and focusing in particular on what we call the parameterization scheme, which are basically representation of subgrid scale features, like, for example, clouds that cannot be resolved explicitly. And now you basically generate a large set of data that is basically having these input-output pairs, and then you basically use this to train a neural network to do exactly what the parameterization scheme did in the first place. And once you've done this, you can replace the parameterization scheme within your model using the neural network. The big question obviously is like, why would you do this? Why would there be a benefit? And the answer is neural networks are normally based on dense linear algebra, very low numerical precision, and they can be ported to whatever hardware you want to work with, because TensorFlow and Google would take care of this. You wouldn't need to do it yourself. And this basically means like, yeah.
I have a question. Wait,
yes,
so you have existing models.
Yeah.
And you're basically using neural networks to make like deep fakes of your models. Is that more or less the idea?
Yeah, we like to call it emulators, but it's basically the idea. Yes, you replace a model component by a neural network, and the neural network is trained from the model component, so it's never going to be better. It's just going to be potentially more efficient, if this makes sense.
Okay. No, thank you.
Yeah.
Sorry.
So it's an efficiency gain. Alex.
Yeah. So when you, I guess if you develop a parameterization scheme, you develop this to work in conjunction with the actual numerical model. So have you done any sort of stability analysis? What happens if you actually just swap out the neural network? Does that sort of wreck your stability of your forecasting model? Do you need to train the parameterization somehow in conjunction with the model? How does it work in practice?
Yeah, that's a sore point. Actually, it works in a sense that most of the people do developments offline, and then they work on it and they get reasonable results and they are really happy, and then they put it back into the model, and then suddenly everything breaks because the model is responding to some sort of feedback. And if this is happening, that's not a good thing, because since you have trained a tool and which is normally a black box, it's also difficult to debug this. So you don't really know exactly what's happening, why the model is crashing, and so on and so forth. So it is not that we have the perfect solution for this, but nowadays, as the emulators are getting better and better, this is less and less of a problem. So we're getting better and better results, and we have now emulators that are actually very stable as well. But it's not for a very satisfying reason. It's not that we basically know we need to follow step A, B, and C, and then everything is going to be fine. It's always going to be stable. It's more like a lot of trial and error testing, which is unsatisfactory. So it's still a little bit work in progress, but for example, in this case, I'm going to talk here. We basically managed to kind of find a very good emulator for the gravity wave track, and we've tested it in a lot of simulations, and we never had stability problems. So it is the case that you can find good emulators and that you can also trust them by experience if you want, but it would be much nicer to have a theoretical description of what's going wrong and how you should actually train those models to make sure that they are stable. Does this answer your question?
Yeah, absolutely. No, that's great. Thank you.
Okay. We're not the first to look into this, so there have been a lot of work going on over the last couple of years on the emulation of parameterization schemes. But we have looked, as I said before, into the gravity wave track parameterization scheme, which is one of the parts. It's basically interacting between waves going, gravity waves born in the atmosphere and propagating upwards in the atmosphere. And at one point, they can't be resolved anymore, so they need to be parameterized. And we actually find very nice relationships between the neural network's complexity and the error that we get, which is good, because this means that we can adjust the neural network error to what we want. We also find that we get a speed up of something like a factor of 10 if we run our emulator on GPUs in comparison to the conventional tool. We don't get the same if we run the emulator within our IFS model yet, but this is going to change hopefully as soon as we switch to GPUs. We can also use the neural networks to generate so-called tangent linear and adjoint model code. So it's very good actually that the algorithmic complexity of the neural network is very small. So you can actually do a lot more manipulations with the parts. And then finally, we are even able to actually reduce the forecast error, because the gravity wave track parameterization that we trained from was higher fidelity than we would use in the normal operational forecast. And therefore, we got a better result in the end. So the results are promising, but as I said earlier, there's still issues with stability in terms of we need to really we need to learn a little bit more how to really be confident that those solutions are always going to work and not just do trial and error testing. You could also think about then improving results in terms of you basically emulate model components that are normally way too expensive to actually be used operationally. And in this context, we looked into what we call three-dimensional cloud effects. So what this is basically you're looking at radiation. So radiation from the sun is coming in, interacting with the atmosphere, in the clouds. A little bit is kind of sent back to space. A little bit is kind of going through to the surface, heating up the surface, and then there's long wave radiation coming from the surface again, interacting with clouds, and a little bit is going up and a little bit is going down. And in this, we typically just represent those fields in a column space, so just a one-dimensional approach in the atmosphere looking up. And we assume that clouds are just two-dimensional layers in this column, which is obviously not correct. And we are able to represent three-dimensional shapes of clouds within the radiation scheme. However, we can't afford to actually do this in operations because it's too expensive. But we can now use machine learning tools to actually emulate the difference between the radiation scheme with three-dimensional clouds and the one without. So we basically try to emulate the difference between the two-dimensional triple cloud scheme that we're using operationally and the so-called Spartacus scheme that is taking care of the three-dimensional effects of clouds. And we actually get quite good results. So this is a study together with David Mayer from University of Reading. And we get quite good results in terms of, if you look at the heating that coming from the three-dimensional cloud effect, on the left side, you will see basically a cross-section through the atmosphere from the South Pole to the North Pole, and the height on the y-axis, and you see the three-dimensional heating of this cross-section due to the clouds for both long-wave and short-wave heating. And the left side is basically the reference, the difference between the two schemes, and the right side is what the neural network is doing. And it's performing well. So it's actually putting the energy where it's supposed to be put, and it doesn't really produce much spurious noise. So that's a good thing. And also, if you think about really the error and the costs that you have, the radiation scheme that we use operationally has a normalized cost of 1 here. The three-dimensional cloud effect has a cost of more than 4 times more expensive, so it's way out of scope for operational use. But the neural network is basically for free. Basically, it is really it's a small neural network and it's just dirt cheap. So we can basically use the combination of our normal conventional tool plus the neural network easily within our forecast system and actually justify the cost there as well. So this is opening also kind of new days and new doors to kind of increase complexity of our models to some extent by making parts of the model cheaper. Also, it's going to be interesting for uncertainty estimation. So for weather prediction, it's not only important that you actually know the most likely scenario, for example, for precipitation 3 days in advance, but it's also really important that you know the distribution. So what's actually the probability that it's going to rain, and what's the probability that it's going to rain more than 10 millimeters and actually may cause some floodings or something like this. And we've performed a study here together with the University of Oxford, where we took our model at 10-kilometer resolution, the IFS model in the first column, and we took observations for precipitation at 1-kilometer resolution, the so-called Nimrod data set over the UK. So in the top line, you will see precipitation fields coming out of our operational model. In the second line, you will see observations from this Nimrod data set. And now the third, fourth, and fifth lines are projections where we basically started from the IFS data and learned to the mapping from the IFS data to the high resolution precipitation fields from the observations. And we use generative adversarial networks. And this basically means that you can generate different situations, how this mapping could be performed. And if you look into the mappings now, you will see that they kind of look fairly realistic. I mean, in terms of like, if you think about the IFS situation, this seems to be a plausible way of actually how the precipitation could look like in the high resolution case. But also you see differences between the different GANs. So you actually are able to generate different realization of this mapping. Excuse me. And this allows you to also learn something about the uncertainty that you have within the model. So you can really also use the machine learning tools here to quantify the uncertainty that you have without the need to run, for example, ensemble models. Talking about ensemble models, yes.
Maybe you finish this slide first. My question was exactly about the ensemble prediction and so on. Maybe
okay, I'll give it a shot. Yeah, I'll go ahead and you give me a shout if you still have the questions afterwards. So normally what we do for uncertainty quantification is that we run our forecast model not only once, but 50 times. So we would basically have a different realization of our model with kind of slightly different random forcing, and then you get 50 answers. And by getting 50 answers, you basically get a probability distribution of a prediction. So if you have a certain uncertainty in the initial conditions, you can change those, but you also add stochastic forcings to the different trajectories. And then for forecast, for example, for temperature, you will get a distribution at the end, given your 50 ensemble members. And that's very important. But it's also expensive. because you increase the cost by a factor of 50 by running 50 ensemble members. So the question is here whether you can actually reduce the cost by using deep learning post-processing. And that's a question that we looked into together with a group of Thorsten Höfler from ETH. And what we've done is we've taken basically a 10-member ensemble as reference, 20 years of data of 10-member ensemble simulations. And then we only used 5 of those ensemble members and basically try to predict this probability distribution at the end using only the 5 ensemble members plus the neural network post-processing. And we do this for 2 different fields, temperature at 850 hectopascal and geopotential height at 500 hectopascal for the 2-day prediction. And we used quite a sophisticated machine learning tool now with ResNets and all sorts of different machine learning layers in principle. Don't want to go into detail here. But now we basically are able to post-process our ensemble. And what we want to improve is what we call the so-called CRPS, the Continuous Rank Probability Score, which is quite a mouthful. But it's basically a way of identifying how good the ensemble was able to predict a probability distribution that is taking into account both the bias, like the mean error of the ensemble, but also the spread of the ensemble. That basically, because you need both of them to be consistent with each other and to be kind of fit to the observations. And what you see here is that if you use a 5-member ensemble, you get a certain result. And if you use 10 ensemble members, you get a different result, which is in principle better. So the CRPS reduced, which is a good sign because the CRPS needs to be as low as possible. However, if you only use 5 ensemble members plus neural network post-processing, you get the blue and the green boxes here. And you see that they are actually able to definitely reduce the CRPS in comparison to the 5-member ensemble, but it was even possible to actually get better scores than when you compared the results to the 10-member ensemble. Why is this possible? Because you do not only adjust the spread and the probability distribution, but you can also reduce the mean error that we calculate by doing error bias correction within your post-processing tool. So it's actually very useful, it seems, to perform machine learning for ensemble post-processing as well. Rüdiger, did this answer your question, or?
I guess partially. I just was wondering, do you still need an ensemble initially to generate the spread and the distributions, and then you apply the machine learning algorithm on this to basically learn this behavior, right?
In this case, yes. So you imply basically the question whether it would also be possible to generate uncertainty from a deterministic prediction, right?
Yes, kind of.
And the answer is yes, you can do that. So in principle, you can think about using machine learning just from a deterministic prediction to predict the uncertainty, and we've done this as well, and it's giving you good results. However, for ensemble, in particular, a couple of days into the future, the ensembles are often underdispersive, which means that the spread of the ensemble trajectories here is much too small in comparison to the error. So if you have a spread like this and the real measurement would be here, then the ensemble wouldn't be very well defined, and you would basically get not a great answer in terms of the uncertainty prediction. And I would assume that many of the application areas for machine learning that would start from deterministic predictions are probably going to be underdispersive. So the spread it's probably going to be very difficult to get the spread right. So having ensembles in the first place for medium range predictions seems to be useful.
Okay, yeah, that answered my question. Thank you.
Okay, I think we're running out of time. So I could stop here and just take any more questions if there are, or I could also babbling on for a couple of more slides, but that's really up to you. Alex, I don't know.
Can you just show us the next few slides before we decide?
Yeah, a preview. Yeah, well, basically we're also doing some work on tropical cyclone detection, so you can also think about how to basically use image recognition tools to detect, for example, certain features like weather fronts, also tropical cyclones. That's useful. You can also do error correction based on surface observations. So you can basically take your global weather prediction model and then compare the simulation with the local weather prediction on the ground and do a little bit more of bias correction. You can try to think about using, for example, machine learning for linear solvers, so also help the dynamical core to get more efficient. You can also think about what's happening if you actually extrapolate into an unseen climate state. And it turns out that actually machine learning tools are really problematic here. So if your climate is changing and you have a deep learning tool, then already for very small toy models, you run into trouble, which is kind of expectable, but this tells you something about the use of machine learning tools in principle for long climate predictions if the weather situations would change drastically. And that's it. Here are my conclusions. And we are going to have a machine learning workshop in spring next year. And if you have, if you would like to join us, it would be great. And if you have want to submit an abstract, it would be even better. And yeah, that's basically me. Thanks.
Yeah, thanks so much, Peter, for this really interesting talk. Lots of stuff going on, and maybe there's some questions and people want to ask something.
May I ask a question? Hamid Yousefi here.
Absolutely.
I guess in terms of long-term prediction, you would need to zoom out and be able to have predictions of the climate and like ice melting, how accurate the models are. And like if you're getting very big errors on those larger scale predictions, then it would be hard to predict the weather long term, right?
Yeah, we typically distinguish here a little bit between weather and climate. So what's happening is weather is an initial value problem. So you start from a specific situation of the atmosphere, and then you run it forward a couple of days, and then you basically get exponential increase of errors, and it's flattening towards climatology. So it's basically at one point, like 15 days into the future, you basically have almost no correlation between your forecast and the real weather situation anymore, because the initial value problem is kind of killing you. Climate simulation is different. So you're actually not interested in a specific weather situation anymore. You're not interested in the weather as the 7th December in 2030, but you're rather interested in whether the general weather in December is going to be warmer or colder in principle. And this basically means that it's easier to predict climate to some extent because it's more like a statistical problem than just the initial value condition. But you still need to make sure that your model is able to kind of represent changes in the predictions. Like if Canada, for example, is seeing heat waves like this year that are just unprecedented, the question is whether if you have learned a machine learning emulator, for example, on today's climate, that this emulator would actually be able to generalize into this new situation. It's actually quite likely that it could, because the weather situation that you then had over Canada, for example, is probably similar to weather situation that has happened maybe in the mid-US 10 years ago or something like this. So in principle, you can generalize to other situations as well, but it's still something you need to be very careful about. Does it answer your question? I'm not sure. Not quite sure.
Not really. So
Okay.
my question was, how good are the predictions? I think it's quite reasonable that it's related. Well, the climate change or ice melt, these are all, you'll have different currents, and the currents are affecting the weather, of course. So predicting the climate and predicting the ice melt, in the long range, if you're predicting the weather in a year, which I assume that you were trying to project over a year, then you would have to look at those other data rather than your initial value problem, which will be very zoomed in. So yeah, my question was, how good are the models now? What is the state of the art in terms of predicting the climate change or ice melt, if you have any information?
Yes, so there are different questions that you want to ask with models in the climate sense. One of them is, for example, what is the mean temperature going to be? Like if you increase CO2, if you double CO2, how much warmer is it going to be? These kind of questions. And their global models are actually not very good to define the error range. So we actually see quite large uncertainties. If we, for example, double the CO2, it could be that we are suddenly end up with a 2-degree warming, or there are scenarios and models where you end up in a 4-degree warming. So it's not very good to answer this question in our models. However, to get tendencies right, for example, is it going to get warmer in northern Canada? Is the Arctic going to is the Arctic going to change more drastically than, for example, the tropics? To get these questions answered, those models are actually capable of, and we see good results in this perspective. But a lot of the time, there are also like tipping points and kind of things where like the dynamics of the Earth is suddenly changing drastically, and those are again difficult to predict. So, for example, for Europe, the Gulf Stream is extremely important, and as long as the Gulf Stream is kind of persistent and similar, The models are probably quite well, but to actually kind of get the point right when the Gulf Stream maybe kind of change the circulation pattern, because in Canada all the ice caps are melting and there's more freshwater and stuff like this, it's kind of more difficult to predict. So it's so and so. It depends on what you want to predict in principle. But I guess the quality of those models has improved significantly over the last couple of years, and like to get tendencies right for like how the weather situation is going to look like in Canada, for example, in 10 years from now, I think they're actually getting really good. But it depends a bit on the question you want to answer. Still not really having answered your question properly, I guess, but
no, it's okay. Thank you for
okay.
sharing. Thank you.
Wait, I think Armin had a question.
Hi, Peter. This is Armin from St. John's.
Hi there.
Thank you for your very nice presentation. I have a very short question. For these models that you have used, I'm talking about a data set. Are these data sets available publicly? I know that you talked about different projects, but because I haven't worked on any models for the climate data set or something, I have no idea. Are they publicly available, or which repository do you recommend for them for one specific, if there's any one specific paper which talks about the available repositories? Modern data, I mean, not the historical data.
Modern, okay. I just wanted to point you towards the historical data because that's easier.
No, but sorry, I'm talking about the modern or historical data, because maybe talked about the last 50 years or the last 40 years, the data set. But if they're available, for example, the last 10 years or something like that, if the terminology was not appropriate, I'm sorry in advance.
So if you're in general interested in data, I would like of the global atmosphere, I would probably look into the so-called ERA 5 reanalysis. It is basically like what we do here is we do data simulation constantly over the last couple of decades, and we basically kind of gain knowledge about the state of the atmosphere at any given space and time over the last couple of decades, and that's freely available from the climate data storage, and really good data. That's, for example, what I use to build my forecast model. Then there's also like benchmark data from based on ERA 5, which is called Weather Bench. That's kind of also coming along with some Python code and to look into if you're more interested in this. And if you're looking into prediction data, then I can recommend to have a look at so-called TIGE data, where there are forecast data from a couple of basically different forecast centers, including ECMWF, and also from the WMO, there's some forecast data provided. But if you have specific questions for specific weather data sets, let me know by email and I can try to answer.
No, I thank you very much. I think you provided very well, you answered very well my question. I don't have any specific about a specific data set, because I told you I haven't used, I'm talking about a statistical perspective of that. So I haven't used the statistical models for the weather data or climate change. So I had no idea about if there's any repository in this case. You answered my question very well. Thank you.
Okay, good. Yeah, we're trying to be. I mean, ECMWF is also pushing a lot of data now into the open data space, because we see that it's really important to make this data available for all sorts of users, and also that we get a benefit out of this if people like you are actually using our data and exploring things. So yeah, we will have more and more data available, but it's an ongoing process, and the data is there's just a lot of data. I mean, we're producing probably 100 terabytes of data every day within the operational prediction, so we can't put everything online. Yeah.
Exactly. Thank you.
Wait, I think Nicolas has a question.
Hi. Yes, I have a question. I have two questions actually. Yeah, so that was like super interesting to learn how like this huge organization is trying to transition to incorporate machine learning. Like that was very exciting to hear about that. But I'm going to ask you like a scientific question. So
yeah.
And it comes up a lot of times. You know, interpretability of these models is a big issue. They're just treated like black boxes. And like you're talking about, you have all kinds of methodologies to make sure that your black boxes are performing adequately and actually they're not, you know, destroying the model or anything like that. And there's kind of like two approaches to this, right? Like there's like sort of the engineering approach where you kind of tweak things and make sure that it doesn't blow up, and you know that's how a lot of things get done. And then there's like, you know, actually trying to understand how these things work. So if it's on like a line, you know, like how much effort is being put to interpretability versus sort of just holding things together and keeping it from blowing up?
50-50.
50-50.
I don't know. I mean, basically, like there are different angles to this. So first of all, what's really important is that you don't develop a machine learning solution for our domain just as a machine learning tool and without any domain knowledge. So it's really important that you get domain scientists involved into projects, because otherwise you're going to build very sophisticated tools, but they're not going to work for the right reason. And also you need to convince forecasters to actually put things into operational models, because otherwise they will just like not trust your tool and not just ignore it if you want. So that's very important. And this is already halfway, if you want, in terms of physical informing, because you get physical feedback, you will get physical understanding of what's happening by working together, basically. If you would ask me where to write a proposal right now in weather and climate and machine learning, I would tell you do it on physics-informed machine learning, because that's kind of it's kind of the hot topic at the moment. And in particular in the US, a lot of people are looking into what they call physics-informed machine learning. They have different definitions of it. So it can be that you just use an ablation study. It can be that you try to basically represent the entire equation correctly, and so on and so forth. So there are different shapes and colors of physics-informed machine learning, but it's a hot topic and a lot of people are working on it. And then on the other hand, there's also the scaling up. I mean, there's also pointing in doing trial and error tests and to kind of just really using a very large machine learning tools that you can maybe not necessarily actually understand what they're doing. So I wouldn't condemn them at all. I would say that it's good to have both approaches in parallel and get going. But there's a lot going on in physics-informed machine learning, trustworthy AI, and these kind of things at the moment. But it's also spinning up still. I mean, it's yeah. Most of the projects have just started within the last year, I would say. So.
Purely sociologically, is there a tension between the two camps, or is everyone happy?
Not yet. Maybe it could be developing, but not yet really. I don't think so.
Okay, I have another question, but I'll let someone else ask. If no one wants to ask, I'm gonna mute myself.
Is there another question, or should just Nicolas go ahead and ask his question?
Okay, I'll ask another question. So one thing that you were talking about was, you know, moving from Fortran and CPUs to Python and GPUs. And like I totally get that, and it's good to modernize these things. It's kind of interesting. So I'm a pure mathematician, so I don't actually do anything useful. But it's interesting how like the available technology kind of influences the direction of machine learning. And you know, GPUs are very good at working with things that are in grids or in these tensor-shaped things, so box-shaped data. And the Earth is a sphere. So I'm just wondering, like, you know, doing like convolutional neural networks on a sphere is a tricky thing. I'm just wondering if you have any experience with things that go wrong in that case, or if you wished that they would have GPUs that were maybe more sphere friendly, or is that even an issue?
So just in general, we have an issue anyway. So if you take machine learning to the side, the amount of the ratio between sustained performance and peak performance that we had in our models decreased drastically within the last decades, which means that nowadays we can only make use of something like 2 or 3% of the peak performance of a given hardware. And this is the reason why we need to go towards this digital revolution, basically trying to also rephrase our models, work with new algorithms and stuff like this. Because in machine learning in principle, you have dense neural networks and you can use a substantial fraction of the peak performance. And that is kind of, it's quite scary. I mean, that if you compare like, this basically means that you kind of may end up very much on the right side of the slides that I've shown you, where machine learning would be much more competitive basically, but just making better use of the hardware. You're perfectly right. So, for example, we're exploring ways like, for example, graphical neural networks right now to actually make sure we can also work with unstructured grids because of the spherical shape. And this is a bit of an issue, and I'm sure it's going to reduce also the efficiency of your machine learning solutions in comparison. But I don't think that's fundamental. I don't think that's going to be the biggest problem. I think it's just something that you need to learn, and there are tools available that can learn this. It's just a matter of time, I guess. Does it answer your question somehow?
So let me try and rephrase that. GPUs and like PyTorch and all that, they're very idiosyncratic tools. They're not all universal. Yep. But they're currently what enables us to use what we have, the hardware, most effectively.
Yeah.
So if I'm using Fortran and GPUs, I just can't get as much performance out of my machinery. So even though these tools aren't perfectly adapted to some of the problems that you have to work with, you're saying that you can get a lot more performance out of your computers by just translating it to that setting.
That's a hope, yes. I mean, there are caveats to it, but I'm pretty sure that, for example, if you would learn the entire model, like the approach that I basically try to convince you that it's not useful, but if you just assume that it's going to be useful, I'm sure you will be at a much higher flop rate than with an existing weather forecast model, for example, just because the weather models are using very different algorithms. They are based on very different stencil sizes. They're using sparse computations. The data loading is a huge issue. Vectorization is difficult. Porting is even more difficult, and so on and so forth. And TensorFlow is doing this for you. So if NVIDIA is using the A100 and it has tensor cores, and you can basically just use matrix multiplication with dense neural networks at half position, it goes like this, right? I mean, that's the difference. And you will lose a lot of performance along the way by being more and more specialized towards the application, but I'm sure you will not end up with the 2% that we have in a conventional tool.
I see. Okay. Thank you.
Maybe I ask a question. I mean, I think you already indicated this a little bit, that this sort of physics-informed machine learning is sort of getting more prominent. So I mean, how do you see this, like, personally as a perspective? I mean, we have, like, say, 100 years of research understanding basically the physics of the atmosphere. We used now for like 70 years numerical weather forecasting based on basically differential equations. And now we toss it basically all away, right? And just use the data alone. I mean, so do you see, like, I mean, I know it's like a too general question to be answered meaningfully, but say, where do you think basically maybe we don't need differential equations anymore? I mean, we are maybe using sort of the physics as an overkill, or there are certain, I guess, processes where we may not even understand the physics properly, right? Like super microscale processes. Yeah. You mentioned nowcasting, right? So like, what's the equation for nowcasting? So can you like comment a little bit on where you think basically like using differential equations may play a role in the future, and where maybe we are actually overusing it and we shouldn't use actually physics-informed machine learning?
I think it's going to be all of this at the same time. I mean, it's not. I mean, I don't think it's going to be just the one machine learning solution killing all and be doing nothing else. And I don't think we're going to have a conventional tool as we have it right now that is basically based on physical knowledge for 95% of the code. I think it's going to be the mixture of it. So I'm pretty sure we will still have a dynamical core solving the Navier-Stokes equation to some extent in the future. But then we also will have machine learning solutions to help even the dynamical core, for example, via preconditioning, for example, via estimations of fluxes through grid cells and stuff like this. I mean, you can combine those two worlds without throwing away all information about the physics behind it, right? And also, if you think about error prediction, I showed you bias correction and uncertainty quantification. Here, machine learning tools can be used from now on, basically, without breaking physics-informed conventional modeling, because if you basically predict errors, those errors cannot really be described with physical models anyway. And if they could, they would have been removed already, right? So there are different ways of how to do this, basically. And also, I mean, what I don't like about the general discussion about physics-informed learning is that there are so many different hybrids of this. I mean, there are so many different ways of how to do this in principle. You could just try to kind of incorporate conservation constraints. You could try to incorporate some sort of physical knowledge about different weather situations. You can try to enforce differential equations and so on and so forth. And for the different application areas for neural networks that I've shown you, you're going to come up with different solutions. So I think at the moment it's really important to explore the space, explore what's going to be useful, and then in the future combine those methods that you have explored in the best possible way. And I'm sure we will see all sorts of different ways of how to kind of combine physics-informed networks with domain knowledge and also conventional numerical tools. I think it's out in the open how to combine this.
Yeah, I think that's a fair answer. Thank you. Thanks a lot. Are there, I know we're going over time, are there any other questions before we wrap things up? Or there is no more questions, then thanks again, Peter, for this really interesting talk and taking the time to answer all our questions, and definitely looking forward to see what's sort of happening at the ECMWF in the years to come here. Thank you.
Thanks a lot for the invitation. It was a pleasure.
Awesome.
Thank you.
See you then. See you, everyone.
Bye-bye.
So.
Bye now.